Hello and welcome to Tribe Topper. In this video session, you are going to learn about combining resistors. So let's talk about the first combination, which is resistors in series. So as you can see here, there are three resistors, R1, R2 and R3. They are all connected in series. So when they are connected in series, we have an end-to-end connection. So the first resistor ends here, the second starts, the second ends here, the third starts. And there is a voltage. We can just assume here to be a voltage of V. So let's say we have here R1, R2 and R3, three resistors, right? So R1, R2 and R3. And we have applied R1, R3. So this is the total potential difference applied. I'll write it as total potential difference applied. Now, due to this, a current I is flowing in the circuit. Since there's just one path to follow, so the same current will flow through R1, then through R2, and then through R3, and same current I will come out. So you have the same current flowing through each one of them. But the potential difference that exists across each one of them is going to be different. So we have V1 across the first resistor, then V2 across the second resistor, and V3 across the third resistor. So our potential difference of V got divided among the three resistors as V1, V2 and V3. So we can say the what you have to remember here is that in a series combination, the the current I through each resistor is same, but the potential difference or the voltage across each resistor is different. So in that case, we will apply the simple formula that therefore V is going to be the sum of V1 plus V2 plus V3, because our V, the total voltage applied, got split up into three parts as V1, V2, V3. So the sum of V1, V2, V3 should be equal to V. Now by Ohm's law, V, the total voltage, is going to be the total current I times the total resistance R. That is equal to I times R1. V2 is going to be I times R2 plus I times R3. So I is same throughout because it's the same current flowing through each resistor and the total current is also the same. So I being common throughout cancels out, and this gives you the direct formula. Therefore, the total or equivalent resistance in a series combination is simply equal to the sum of the three resistors. So R total is equal to R1 plus R2 plus R3. Now what happens in the resistors in parallel combination? So in parallel combination, it is like one after the other, not just consecutively one after the other. Like you sit in a theater, like one sit in the first row, the other sit in the second row, the other sit in the third row. So all of them will have their starting point meeting here together. All of them, resistors R1, R2, R3, have the starting points here and the end points connected here. So that's a parallel combination. In parallel combination, you must remember that this time your V, the potential difference across each resistor, is going to be same, right? So this time the potential difference across each resistor is same, but now your current has three paths to follow. So it was coming as to be I, the total current that enters, but this gets split up as I1, then I2 and I3 among the three resistors. So I would say, but I would be different across each resistor this time. So in the last time it was V which was different across each resistor, but this time it is I which is different across each resistor, but the potential difference V is going to be same. So that means this time the equation applies that I is equal to the sum of I1 plus I2 plus I3. So just remember that all the three are going to add up here and come out as I again. So I is equal to I1 plus I2 plus I3. So by Ohm's law, if V is IR, then I is V by R. So it's V over R total. That's going to be equal to V by R1 plus V by R2 plus V by R3. And V being common throughout cancels out. So you have a formula for the total resistance in parallel to be R total is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So if you take the LCM, you're going to get R1, R2, R3 is going to be equal to R2, R3 plus R1, R3 plus R1, R2. This is 1 by R total. In the end, don't forget to take the reciprocal. So we'll say, therefore, what's R total? That's going to be the reciprocal of this. So it's R1, R2, R3 upon the entire combination R1, R2 plus R2, R3 plus R3, R1. So in parallel combination, because your formula is 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3, in the end, don't forget to take the reciprocal. Okay, so let's try how to find the total resistance of the circuit shown in the figure below. Okay, so in this circuit, if you look at it carefully, the first combination, this one, let's say this is one combination A, I'll put a bracket here, and this is the other combination B, other resistor. So the first combination is two resistors in parallel. So we can find out their total resistance and consider it to be a single resistor. So what will be the total resistance of 2 ohms and 3 ohms? So we'll first find out Rp, the resistance in parallel. So that's 1 by Rp is equal to 1 by 2 plus 1 by 3. And the LCM here is 6. So I get 3 plus 2. That's 5 by 6. Therefore, Rp is equal to 6 over 5. And that gives me 1.2 ohms. So Rp, this total resistance is 1.2 ohms. So we can replace the circuit that this whole thing is equivalent to one resistance of 1.2 ohms out of these two, 2 and 3. And this is in series with the next one, which is 1.8 ohms. So therefore, these two now can simply be added. So the total resistance is equal to this 1.2 ohms which we got from the first combination of parallel. This is now in series with the second resistance of 1.8 ohms. So we get a total of 3 ohms as the total resistance of this circuit. Now to find the total current and the part dissipated in each of the resistors, first we'll have to of course find the total current in the circuit. So total current in the circuit is going to be how much? We have V is equal to IR. So I is equal to V by R. So or R total. So V, that potential difference applied here is 6 volt upon R total that we have here is 3 ohms, right? So this gives us a total current of 2 amps. Now this 2 amps is going to be divided among these two combinations. So to find that out, let's see how this total 6 volt is divided among these three resistors. See, these two are in parallel, so we will have one voltage existing which will be same across these two, and one voltage will be given to this part. So let's say that's V2. So we can easily find out the voltage across 1.8 ohms because the current, the total current 2 amps that has entered here will leave from this combination and enter the 2 amps will enter the 1.8 ohms resistance. So therefore, what will be the voltage across the 1.8 ohm resistor? That is going to be equal to IR. So I that enters here is 2 amps times 1.8. So out of the total 6 volt, 3.6 amperes is given to this resistor. So how much is left for this parallel combination? Therefore, voltage that exists across the parallel combination is equal to, out of 6 volt, you subtract 3.6, and you get 2.4 volts. Now we have the voltage that is existing across this 2 ohm and 3 ohm combination, and that voltage is 2.4 volt. So now we can find out the power dissipated in each of these resistors. Now, since these two resistors are in parallel, so they have this common voltage, therefore the power P1 across the first resistor, that is of 2 ohms. So power P1 across 2 ohm is equal to V square upon R, which is equal to 2.4 square upon, I will say R1, that is 2 ohms. And solving this, we get 2.9 watt. And P2, the power across your resistor of 3 ohms is equal to again V square by R 2. So that's 2.4 square by 3, and solving this we get 1.9 watt. So we got the power that exists across the each resistor using the formula of V square by R. So that is all in this video session. In the next video session, we are going to talk about potential dividers. Thank you.